we're going to talk about synchronous motors and the effect it has on a motor block load. This is AC theory, but this is where we're getting into the AC effects of a synchronous motor or power factor correction. So let's talk about a synchronous motor first. This is from a website that does not belong to me, and so I'm using it for educational purposes, and it is from the ABCs of Synchronous Motors. It's a website, and so like that. So I've given proper credit to whoever created this website, and it has a lot of good information about synchronous motors. And we're going to go over some of this stuff. If I ever get the top back where it's supposed to be. Synchronous motors are pretty efficient. They have a unique and very efficient electrical drive in the industry. They perform with great economy while converting electric power to mechanical power. They can be built with unique physical features. Synchronous motors can be designed to effectively operate over a wide range of speeds to provide the best drive for a wide variety of loads. Power factor corrections. They can be at 100% power factor correction fairly easily. They can operate at leading power factors by overdriving the motor's excitation field. So they can help reduce your power cost and improve efficiency of a whole bank of motors, and that's what we're going to talk about today. Reduce maintenance, space savings, constant speed can be an advantage. Whoops, a little too much there. Because they turn, as you know, synchronously, meaning at the speed of the rotating magnetic field, because they're locked up. They don't have slip. This is an induction motor that does not have slip. Okay? Adjustable speed means lower power costs. In many cases, more economical to operate driven equipment at reduced speeds, and that's true. So you can vary the speed of a synchronous motor. So they're pretty advantageous motors, right? All right. Let me get out of this thing. And let's go back to my little slideshow here. And so we're going to do some cost-saving calculations. And we're going to add, what we're going to do is we're going to have a bank of motors, and we're going to calculate it first, what it's going to cost in apparent power, because apparent power is what you pay for, right? And we're going to look at some fairly large motors, and let's look at a bank where we have a 277 480 power supply, and we've got a 25 horsepower motor that draws 34 amps. We've got a 30 horsepower motor that draws 40 amps, 40 horsepower that draws 52 amps, and a 50 horsepower motor that draws 65 amps. Okay, so fairly easily we can calculate this total load, right? So let's look at the true power that they're creating. How much power is 25 horsepower in watts? How much true power is 30 horsepower, 40 horsepower, and 50 horsepower? So one of the things we want to do first, before we move on, is we want to find the power factor of all these motors. All right? And we've calculated this kind of stuff before. And we're going to do that again real quick. So I'm going to pause the recording while we do the calculations real quick for the power factor and how much total apparent power this bank is using. And how do we find the total apparent power? We add up all the true power, add up all the VARs, and find that total apparent power hypotenuse for the whole bank. So let's do some calculations and then we'll come back to this. All right, what we've calculated out is that for motor 1 we have a true power of 650 watts, And why does it keep changing that to VA? Anyway, 267 VAs. And why does it keep doing that? Don't, please. Oh, shoot. Now where am I? All right, one more time. In motor 1, we have a true power of 650 watts, an apparent power of 28,267 VAs, and that gives us a 48.7169 degree angle with a 65.97% power factor. In motor 2, we have 22,380 watts and 33,255 VAs, which gives us a 47.7024 degree angle that gives us a 67.29% power factor. Motor 3 has 29,840 watts and 43,231.98 VAs, giving us a 46.3516 degree angle, and that gives us about a 69% power factor. And motor 4 is about the same. It has 37,300 watts and 54,039.98 VAs. And again, that's a 46.3517, only slightly different. And that's about a 69% power factor also. So knowing that, we now need to figure out our VARs. Because what we're going to do to get our total apparent power for this load bank, we now need to add up our VARs. So let's stop and calculate out the VARs. Okay, so we find the VARs, and we know that the sine of the angle times the hypotenuse gives the side opposite. So we're going to take the sine of the first motor, multiply it times its apparent power, and we find 21,241 VARs. We take the sine of the second angle for the second motor and multiply it times its apparent power to find that we have 24,597 VARs. On our third motor, we take the sine of that angle and multiply it times that apparent power, and we get 31,282 VARs. And on the fourth motor, we find that we have the sine of the angle times 54,039.98 VAs gives us 39,102.8 VARs. Okay, now what we're going to do now is we're going to add up all these VARs and all the watts, and we're going to have all the watts become a single angle side adjacent, and the VARs will form a single angle side opposite, and then we will take the tangent of that, find the total angle, and that's the total phase angle for the total motor block. Okay, so let's do that now. Okay, so now we're going to look at our total power for our total bank, and we find a total of 116,223 VARs and 170,000 watts. And now we need to calculate the hypotenuse from that, and we're going to do that now. And I'm going to hit pause again and while we calculate that real quick. Okay, so we found our apparent power, 158,171.95 VAs, and that's the power that we're going to be paying for, right? Now, what if we take one of those motors out and we put in a synchronous motor and we overdrive it so that it becomes a leading power factor angle. So now what we're going to have is we're going to have the same calculations we had before, except our current, we're going to replace the third motor, the 40 horsepower motor, with a synchronous motor. And we're going to see how that affects everything. And what it's going to do to our calculations is this motor has negative VARs, basically. It has VARs that are leading instead of lagging, because before we were calculating all lagging. So now the exact same calculations are going to happen, except we're going to change 1 for motor 3. And we're going to take away all the VARs that it supplies at that power factor. So we have to find its power factor. We have to find out how many VARs it's producing. And we're going to subtract that from our total VARs, and we're going to come up with a new apparent power. Okay, can we do that now? Let's give that a try. All right, so this time we have our new triangle. Have I talked about that already? Uh-oh. Okay, so we did motor 3 only, and we found we had the same true power was 29,840 watts. We found that we had 34,086.75 VAs, and we had a phase angle of 28.9 degrees, and we had a power factor of 87%. So we want to find the VAR. So we find the side opposite by multiplying the sine of the angle times the hypotenuse. The sine of this angle is about 0.4832, so we're going to multiply that times the apparent power, 38,086.75, to find that our VARs are 16,473 VARs. So now we're going to go down and we're going to come up with a new list of VARs, except our motor 3 VARs are going to be subtracted from the total instead of added to the total. So now we're going to add 21,241 VARs, 24,597, and 39,102.8 VARs. We're going to add that all up, and then we're going to subtract 16,473.5 VARs. Now let's find that. Okay, so our new total VARs for the whole unit is we get 84,940.8 lagging VARs, and we have 16,473.5 leading VARs. So we're going to subtract the leading from the lagging for a total of 68,467.3 total VARs. Now we're going to recalculate our total triangle for our total load and find our new apparent power. All right, so our total bank power. We find that we have 68,467.3 VARs, 108,170 watts, and that gives us it describes a 32.33 degree angle and a power factor of 84.49%. And we can find that the apparent power is the true power divided by the power factor. So we can divide 108,170 by 84.49%, and that'll give us 128,145. 014, my apologies. .57 VAs. So we have a new apparent power. Now this is what we're paying for, 128,114, I'm sorry, 128,014.5 VAs. That's 128.014 kVA, and our previous power was 158.7 kVA. Now, if you know that you're paying, now that's per hour, right? These motors are running 8 hours a day, right? 50 weeks a year, about 2,000 hours a year. So if that's the case, what is the cost savings of just installing this synchronous motor instead of another induction motor? Let me tell you those numbers again. Now this is per hour. This is per hour. Okay? Previously, we were burning 158.771 kVAs. And now we're burning 128.014 kVAs per hour. 2,000 hours a year at a cost of 20 cents per kVA. What is the savings per year of installing the synchronous motor? Do figure that out. That's the end of the broadcast for today, and thank you for tuning in.